In this video, let's very quickly explore and understand this concept of conditional independence. We will also compare conditional independence with unconditional independence, something which we refer to as just independence. The unconditional aspect is taken for granted. It's not explicitly mentioned. Okay? So, what is independence of two events? When are two events A and B independent? Well, they are independent if the knowledge of occurrence of one of the two events does not in any way affect the probability of occurrence of the other event. Okay, so mathematically, if let's say my focus is probability of event A and I am given this extra piece of information, I am given this knowledge that event B has happened, which means I am in a position to estimate this conditional probability of A given B. If A and B are independent, then this conditional probability will still be equal to the unconditional probability of event A. Okay, this piece of information that B has happened was completely useless in determining, or let's say altering, the probability of event A. Okay, and this happens when A and B are independent. Alternatively, if let's say my focus was probability of event B, then mathematically I can write down this fact that A and B are independent by writing down the probability of B given a conditional probability, to be actually equal to just the probability of B, an unconditional probability. This piece of information that event A has happened was completely useless in terms of determining, or let's say altering, an already known probability of event B. Okay, so this is one way of mathematically expressing this notion that A and B are independent. Well, there's one more way of expressing the same thing, and that's a way which we love to memorize, and that's in terms of joint probabilities. So joint probability of A and B, written as probability of A intersection B, in general can be written as probability of A that times the probability of B given A. That's one way of writing down probability of A and B. Please note that this way of writing down this joint probability does not in any ways depends on the dependence versus independence of events A and B. This thing holds in general. Alternatively, I could have written this guy down as probability of B this times the probability of A given B. Okay, and now if I were to introduce this notion that A and B are independent, that means I go back to this box which I created. I can pick from this box the probability of B given A to be just probability of B, and probability of A given B to be just probability of A. Okay, so irrespective of how I write down this general formula, both of these ways are pointing to the same result, and that is, if A and B are independent, the joint probability of A and B is simply written as the product of their respective unconditional probabilities. Okay, probability of A and B is simply probability of A times probability of B. Now, let's move on to the focus of this video, and that is conditional independence. So if I'm talking about conditional independence, it has to be conditional upon something. For that purpose, let me introduce another event, and that is event C. I am retaining the two events A and B, and I am introducing another event C. Let's start by very quickly stating the verbal definition of conditional independence. Two events A and B, they are said to be conditionally independent given event C if the occurrence of one of the two, that means occurrence of either of A or B, does not in any ways affect the conditional probability of the other given event C. Okay, see, it's a verbal definition which is very similar to the definition which we had for unconditional independence. The only notable difference is that we are conditioning everything on this event C, and therefore we are moving from unconditional probabilities to conditional probabilities given event C. Okay, so if I had to write down an equation that looks something like this equation, let's try and do that. If in this world I am operating under this assumption that event C has happened, then let me assume that my focus to begin with is the conditional probability of A given C. If I were to serve you with this extra information that B has also happened, what does it mean? It means that I was already assuming that C has happened, and you are now telling me that B has also happened, right? In the light of this information that both B and C have happened, if A and B are conditionally independent given C, this information that B has happened is actually useless in determining, or let's say altering, this conditional probability of A given C. Therefore, this guy can simply be written as probability of A given C. What has changed? It's essentially this equation in which on both the left hand side and the right hand side I have introduced the given C. Right? This is given C, this is also given C. Okay, that's what has changed. Okay, so alternatively, if the focus of mine was probability of B given C, and I were to tell you that A has also happened, if A and B are conditionally independent given C, this piece of information is actually useless. And therefore, this conditional probability is just the same as probability of B given C. Okay, this guy gave us no additional or useful information. This is essentially conditional independence, a very simple concept in which we are conditioning everything upon this event C. Okay, the same way as we extended this box to an alternate definition which was in terms of joint probability, I can extend this box to an alternate definition which is again in terms of joint probability. But this time it's a joint probability of A and B given the event C has happened. Okay, so if I were to not assume anything, then what would this be? In general, this can be written as probability of A given C. See, C has already happened, so we can't deny that. Let's begin by A happening. So A given C, that times now B happening given both A and C have happened. This is one way of writing this joint probability. Okay, the other way of writing down this joint probability will be, let C has already happened, let B happen first. So probability of B given C, that times the probability of A happening given now B and C both have happened. Okay, again go back to this box. This box is telling me that actually I need this guy. So this guy is just this guy. So probability of B given C. What is this guy from our box? It's actually just this guy. So it's probability of A given C. Okay, so what is it telling me? Both of these, they are telling me that the joint probability of A and B given C has happened if A and B are independent can be written as the product of two conditional probabilities this time. The probability of A given C and the probability of B given C. See, you can very easily draw parallels between the equations that we've written in the box and what these equations imply in terms of joint probability. See, this is essentially the same as what we had here. It is just that I have replaced unconditional probability with conditional probability given event C. Okay, so my takeaways are these. Okay, so A and B are conditionally independent given event C if all these three hold. So before we stop, let us very quickly apply what we've just learned to a simple solved example. So we have our events A and B and we are conditioning upon event C. Okay, so we've drawn out a Venn diagram and we have very clearly also written down the probabilities. Okay, various probabilities. For example, this is the probability of A and B and C. This 2% plus 5% is the probability of A and C, and so on. Okay, so let's do this. Let's first check if A and B are unconditionally independent or not. What is probability of event A? It is simply 4% plus 7%, 11% plus 7%, so 18%. So probability of event A is 18%. Probability of event B, 12 plus 4, 16 plus 2, 18 plus 6, 24%. Okay, what is the probability of A and B? Well, this Venn diagram tells me it is 6%, 4 plus 2. Okay, I'm only taking into account this overlapping region between A and B. So this diagram is telling me it's 6%. If A and B were independent, then this guy should have been the product of these two. Okay, which doesn't seem to be true in this case. So this tells me that events A and B are actually dependent. And now let's very quickly check if A and B are conditionally independent or dependent given event C. So everything switches from unconditional probabilities to conditional probabilities given event C. Okay, so probability of A and B given event C, what will this be? It will very simply be equal to probability of this guy and this guy, so A and B and C divided by probability of this guy, so probability of C. This diagram tells me this is the probability of A and B and C, that's 2%. What is probability of C? 15 plus 6, 21 plus 7, 28. Okay, so this is actually 1 over 14. So what is probability of A given C? A given C. It is basically probability of A and C that divided by probability of C. What is probability of A and C? This overlapping region, 2 plus 5, so 7%. Okay, divided by what is probability of C? It's 28%. So this is 1 over 4. Next, coming on to probability of B given C, that is probability of B and C divided by probability of C. Probability of B and C, well, that's this overlapping region, 6 plus 2, 8%. That divided by probability of C, that's 28%. So this is essentially 2 over 7. Okay, so multiplying these two actually does give me 1 over 14. Okay, so this condition is satisfied. See, so it's this numerical example is telling me that while A and B are unconditionally dependent, A and B are conditionally independent given event C. What we've established using this solved example is one more takeaway for you to remember, and that is conditional independence and unconditional independence do not imply each other. Like we had in this particular solved example, A and B were indeed conditionally independent given event C, but A and B were not unconditionally independent. Okay, the opposite is also true. You can easily cook up an example in which A and B are actually independent, but conditionally A and B may be dependent. Okay, so this video was about understanding this concept of conditional independence.